So we're going to pick up from our lecture last time, last time we were talking about, and broadly speaking, kind of the three areas that we discuss and talk about in psychology classes, which includes content, so general information about what we know about human behavior and how we know it and how that applies to our day-to-day life. Definitional, so basically just learning terminology and definitions to help us be able to communicate clearly and understand what those words mean and also have an idea of how they fit into the broader picture. And then methodologically, what are the methods and what are the techniques we use to get to that content? So basically, what we're really interested in, at least most of us, is the actual content. What do we know about human behavior and how can we apply it to our own lives? And that often are the better stories of psychology, if you will. The stories of how these studies occurred and what they tell us and how they generalize and how we can trust them, kind of internal and external validity. But we also need to just learn the terminology, the definitions, to be able to communicate cleanly. And then the methodology, which I also referred to as kind of models to help us understand and categorize what we're doing, and to be able to understand and categorize the research that we read. And of course, when we're talking about this class, Psych 220 and Psych 221, Research Methods and Statistics, we're really not focused very often on content. We're mainly focused on terminology and definitions, the methodology, and the models that we use to kind of conceptualize that methodology. And one of the things I've repeated over and over again is that when we talk about whether or not we can talk about causation and whether we really have a strong argument that we have discovered something about human behavior, we're often needing to look at not the statistics used. We want to make sure that they're appropriate statistics, but we're more interested in what was the methodology used to make those arguments within the study itself. It's one of the reasons that the research paper is so important. The paper has a lot of heavy lifting to do. The paper is telling us what research has come before, what we already know, what this particular research study is trying to address. The methodology is then going to describe the study in detail, enough that we could replicate or close to replicate it ourselves without even access to the appendices. But also it gives us information about what was the methodology they used. What did they do to establish internal validity? What did they do to establish external validity and how they sampled? And then finally, the statistics of what was actually found. How reliable is it? How big was that effect? How meaningful was that effect? And also whether it's obviously statistically significant. In other words, the probability of it actually just being due to random chance or error. And finally, the discussion is where we put that all back together. So we're going to continue talking about models within methodology. And what I mean by models within methodology are ways to categorize the methodology we use when we do research and studies in psychology. And we were talking about specifically between and within participant designs in our previous lecture. And again, between participant designs are when there are different people in each one of our conditions. Within participant designs is when the same people are exposed to all conditions. So again, as a quick example, if I have an independent variable where you're exposed to nothing, you're exposed to a study guide, you're exposed to a study guide and weekly study sessions. So those are my three conditions. In other words, no help studying for a test, just a study guide, or a study guide with weekly guided sessions. That would be group 1, 2, and 3. If I was using a between participants design, I would randomly assign everyone in a class, let's say an N of 60 people in my class, randomly to those three conditions. So approximately a third of the students would get no study guide at all. About a third would get the study guide, group 2, and the other third would get the study guide and access to those weekly study sessions. That would be group 3. Another way I could do this is a within participant design, where all 60 students for the first test get nothing. They're now the control group. 4 weeks later, all students get a study guide, but that's it for the second test. And then finally, in the third condition, at the third test, 4 weeks even later, test 3, they're given a study guide in those weekly sessions. Now you can see that the advantage here is that I've pretty much tripled my sample size. Both studies have 60 participants, but in one of them there's only 20 participants in each condition. In the other case, I've got 60 participants in all conditions. Not only that, the within participant design, I don't have to worry about individual differences because the people in my three conditions are always the same people. Now, I have opened myself up to some new problems. Is test 1, 2, and 3 equally hard? And are the students learning more and more about the class as they move from test 1 to test 2 to test 3? In other words, are they maturing naturally, regardless of whether I give them a study guide or not? And most students, by the way, do tend to perform better on each test because you also learn what the tests look like. Most professors kind of have their own idiosyncrasies on how they give tests, what those tests look like, and usually they don't vary much from test to test. The content may vary, but kind of the format tends to stay the same. I know that's the way I am, which means that also you probably are going to get a little better on each test just because you're a little more familiar with what's coming up. So we're going to be talking about power and within these between and within participant designs and how they affect statistical significance. So again, as a reminder, we're talking about an experimental study. And in an experimental study, we have some requirements. We're trying to get at causation, and to get to causation, we need temporal precedence, we need that statistical relationship to begin with, and we need to rule out any other potential cause. And two of the biggest tools we use to try to get at causation is that we take direct control of the IV. In other words, we assign people to conditions within our study. That assignment is usually through random assignment, which allows us to basically, hopefully, statistically average out individual differences. And generally speaking, within the methodology and statistics we're talking about in this class, we're really talking about experiments where the independent variable is categorical. In other words, it has levels, conditions, or groups, and the DV is continuous. And the most simple of experiments is what we often refer to, if you want to get technical, is as a post-test only control group design. What that means is that we start with a sample. Now, how we got that sample is going to affect our ability to externally generalize, but once we have the sample, the question becomes internal validity. What did we do with the sample? Well, what we did was randomly assign them. So there was an equal chance of each participant ending up in one of our two groups in this case. Half of those participants are put in the control group, and the treatment in the control group is no treatment whatsoever. The other half, approximately, because this is random, are sent into the experimental group, where they're presented the treatment. Well, in this case, let's say it's a study guide. And now we don't actually check to see were these two groups equal to begin with. In other words, there's no pre-test. A pre-test would mean that before I even do the treatment, I give them both a general knowledge test to check, did random assignment work? Did my two conditions basically have the same score prior to treatment? But we didn't do that in this case. We made a very simple study. We did random assignment. Half of our condition is in the treatment group where they're getting the study guide. The other half is in the control group where they don't. And then I have a post-test, the test. And what I'm looking for is I'm assuming that if a random assignment did its job and that the two groups are roughly equal on all individual categorizations, including their ability and their knowledge of the material, and then one group got a intervention, the study guide, and that group then performed statistically better than the control group, I have made a pretty decent argument that I have a fairly tight, internally valid study that shows that study guides have effect on performance. But when we're wanting to do this, remember, we want to be as powerful as we can be while still being realistic. So we did talk in the previous lecture about kind of mundane realism and experimental realism. So when we're thinking about power, one of the things you do want to keep in mind is as you strive to be as powerful as you can be, try to make sure you're also not making a truly unrealistic study. So some of the things we can do to increase the power, and when we talk about power, the terminology power refers to our ability to detect effect. So the larger and more powerful a study is, the more likely it will find a smaller and smaller effect if it's there, and declare it statistically significant, basically that we're at least 95% sure that that effect exists. The most easy way to increase power, where you don't really have to worry about anything as far as potential other effects to your study, is to simply increase the sample size. And this is probably one of the first tools we always want to use, because also as we increase sample size, we may also be helping external validity. So increasing sample size within reason and within our ability and resources to do is always generally a good idea. The larger our sample size, the easier it is to find smaller effects. In other words, the more powerful the study. Also, as we increase sample size, we potentially are making a better and better argument that we can generalize because we have a larger sample. We definitely want to eliminate unwanted variance within our study. So we talked about confounds and individual differences. Individual differences can often be countered with random assignment, but another way to do it is with post-pretest. In other words, we want to use random assignment and then check our random assignment. We want to basically give our outcome variable prior to any kind of treatment or assignment to group other than the fact they've already been assigned. So in other words, are our groups equal on the outcome prior to whatever manipulations we're doing with the IV? Remember that the terminology of confound is specifically, it is a variable that varies with our IV and could potentially impact our DV. So we really want to think through when we're designing a study, is there anything else that's varying from condition to condition that is comorbid, if you will, or related to our IV? If so, if we can eliminate it, we want to, because confounds seriously reduce the power of our study. We obviously can also think about our intervention itself, our IV. So how are we actually interacting and impacting that IV? How are we defining that IV? The bigger the difference between the levels of IV, generally the easier it is to find effects. We also want to make sure that we focus our participants' attention on that IV. We want to make sure that it's salient to them. And within that, though, we also want to ask ourselves, are we creating kind of a false dichotomy, if you will? And some of the more famous studies in psychology actually are a little guilty of this. The initial studies on obedience, where we were actually looking at groups of people, where only one person in that group actually was the participant, everyone else was an actor, and they were basically doing line size comparisons. So basically they were being presented with 3 lines, and each participant in turn was asked which line was of an equal length. Well, the first time through, everyone gave the right answer. But from that point on, the actors who all went before the participant would give the wrong answer. And what they found was that most of the time, the person that was in the last very quickly would start to go ahead and give a wrong answer too. In other words, they didn't want to go against the group. Now, this was actually fairly artificial and a big difference. There was no question that these line answers were wrong, but it was also an initial study. So one of the criticisms of that study was that they had gone so far into making sure there was a huge difference between the levels of their IV, and that they made sure to focus participants' attention on that IV, that it also was unrealistic. It lacked mundane realism. So again, we just want to think about how much can we make sure that our IV levels truly differ while still keeping in mind whether or not it's a realistic difference. And of course, we always want to make sure that the DV, our outcome, not only measures what we think it's measuring, but is also a reliable measure of that construct. Now, another way we can check this, and we talked about this also in the last lecture, is pilot studies. Basically a trial run before the actual study. We run the study components with a very small sample, not necessarily to find an effect, but to ask the questions, are the differences between my IVs and big enough? Do I need to increase them, or are they too big? Do I need to maybe scale them back a little bit? It also allows us to watch the study in real time, which can help us sometimes identify confounds that we didn't at first think our way through. We might notice a difference that's occurring between our conditions that we hadn't caught initially. We can also kind of ask ourselves, what's the mundane realism? What's the experimental realism? So remember, mundane realism is our study actually looks like the real world. Experimental realism means it may not look like the real world, but people are still getting engaged with the study. We may also find out that though we thought our IV was very obvious, people aren't attending to it. So we can catch mistakes in how we're giving instructions, whether people are getting confused by the study. We can look for potential confounds, and we will get a data set with this. It'll be a small one, but we can actually take a quick look. Are we starting to at least see evidence of the effects that we're looking for? So are people attending to that IV? Are people varying on the DV? So we have the potential of ceiling or floor effects? Is the DV truly capturing variance? Because if that DV, if everyone on a 1 to 5 scale says 5, you're never going to find a statistical difference because you're getting ceiling effects. If everyone on a 1 to 5 DV scale always says a 1, you're not going to find anything because you're getting floor effects. You need to find variance. Most people scoring somewhere in the middle of that DV, and then basically having a normal distribution on either side. So that's another thing we can check in a pilot study. So what we're really worried about beyond actually setting up the initial methodology of our study is we're wanting to get rid of those confounds. So they're both extraneous and confounding variable. It's not your IV, it's not your DV, but it's an additional variable that varies with your IV and potentially could affect your DV. So if you can make an argument based on past research and logic that yes, something is varying with your IV, let's for say example that when people come to your study, you randomly assign them to one of three conditions, and then they go to three different rooms to actually be exposed to those three different conditions. If those rooms are all in the same building, approximately the same size, slight variances, you might make an argument that yes, this potentially is confounding, but there isn't a major difference. Now, if those three rooms are vastly different, one of them's across campus, so those participants, not only are they randomly assigned, but in two conditions, participants go 20 feet and start the study. But in one condition, people have to cross campus to start their study. That potentially could be a stronger argument that there is now something fundamentally different between your three groups. So again, you want to eliminate confounds methodologically if at all possible, and if you can't, you want to at least identify them and measure for them. And again, we have to ask ourselves, is it a confound or is it an extraneous variable? Extraneous variables have an effect on the DV, but it's not varying with the IV, and it's not due to the IV. So a true confound changes systematically with the IV and DV, and because of that, we cannot separate its effects from the DV on the IV's effect on that DV. In other words, we really don't know. It happened, and it may also be an alternate explanation. So again, if we're truly designing a study that we can trust, we want to make sure that we have a cause that we're manipulating, and that's what we are actually inducing. We're creating that cause, we're assigning people to those groups, and we're doing that to establish temporal precedence. And then we're hoping that there is no other variance that's occurring outside of our intervention, that IV, and then our outcome measure, the DV. If there's any other factors, those are our confounding variables. If they're related to both our IV and DV, they're a confound. If they're only related to the DV, they become more, they're still a problem, but they're not necessarily as big of a problem. They're what we consider to be noise. Noise are factors that do not vary with our IV, but still may impact our outcome. So for example, if I'm doing a study on aggression, we know temperature affects aggression. The hotter it is, we tend to be more irritated. The more irritated we are, the more aggressive we become. So if I'm running an intervention that's trying to vary levels of aggression, and unfortunately the air conditioning has given out in the middle of summer in the building I'm running the study, and all the rooms are 90 degrees. That's noise. It's probably going to make it harder for me to find an effect because even my baseline condition, which is my control, is probably going to be more aggressive than normal. So that becomes basically just kind of static that makes it harder for me to find the effect I'm looking for. So ideally, we want to have neither confounds or noise in our study if we can avoid them. So how do we control for these extraneous confounding variables? The first one is basically we want to ask, is it a confound or is it simply extraneous variables? Extraneous variables, again, are noise. Environmental. So you want to ask yourself, with what I'm interested in researching, has there been past studies that have found environmental effects? And if there have been, and environmental effects can be temperature, they can be wall color, they can be exposure to noises, pretty much anything that's going on in the environment. If there is, we want to make sure that we attend to those environmental differences and remove them if possible. Has there been past studies that have shown that individual differences can strongly affect my outcome? So, for example, if my outcome is test performance, there is no question that your education level and your success in education, are you an A, B, C, or D student, will probably impact also how well you do on the test. Now, I can make an argument that if I have a study guide that's supposed to increase performance, it may increase performance no matter what your skill level. But again, those are potential individual differences. So one of the ways I can get rid of that is hopefully random assignment. And if I'm really wanting to make sure I got rid of it, it would be random assignment and then a pre-test prior to my intervention and post-test. Or if I can't use random assignment, I may try to identify the major individual differences that may also be related to my DV, and I can do this through the lit review and actually measure them to potentially remove their variance later in the statistical analysis. And also recognize that sometimes when we're trying to avoid environmental or individual differences, we may create time-related noise. Fatigue, studies that go on too long. Practice effects, people taking the study over and over and over again. And this often occurs within participant designs where your participants are going through all conditions. Ways to control confound specifically is to try to hold the variables constant. So more environmental controls, basically making sure everyone's being exposed to pretty much the exact same conditions, exact same time, exact same temperature. If you can't use random assignment, consider matching on individual differences that the research and past research has suggested may influence your dependent variable. You can definitely, hopefully, use randomization of IV conditions, especially in a time-related study. So this is going to be a within participant design where we're worried about fatigue. So every participant is going to be exposed to all levels of my IV. I may want to set up a situation where randomly some of them are exposed to the first condition, some of them are exposed to the second condition first, and some of them are exposed to the third condition first. In other words, I want to vary when they encounter my IV levels to help me say that there's not a fatigue factor, or if it is, it's balanced out across all my conditions. And obviously, again, our biggest tool and our best tool to get rid of a lot of these extraneous and confounding variables is random assignment when we can use it. So let's talk about that random assignment. Random assignment is done to control for extraneous variables influence that might have an impact on the results. And in fact, using random assignment often gets rid of a lot of the potential problems that we would have with this problem. The idea here is, again, that however we grabbed our sample from our population, once they're in our study, once they've been defined as a participant that is going to participate in our study, then every person within that sample has an equal chance of being assigned to any particular condition or level of our IV or IVs. In other words, they are randomly assigned to every potential group that we've created with our IV or IVs.